In calculus, we deal a lot with curves in the xy plane. And often the way we describe these curves is with using functions. So you might have y as a function of x, and that would produce a certain curve in the xy plane. But the problem with functions is that they are limited. If we were to instead want to try to describe another curve, say we're trying to describe this ellipse, that couldn't be described as a function. And the problem with that, of course, is that it does not pass the vertical line test. So there's no function. Now there is a formula, of course, for an ellipse. X squared over a squared plus y squared over b squared is 1. That would get you this particular ellipse. But in general, we are very limited with what we can describe just using functions or equations of x and y. And sometimes we need other tools to help us solve these sorts of problems. So here's what we can do. Rather than worrying so much about what the function or equation is that describe these particular curves in space, instead, what we will do is imagine ourselves traveling along these curves. So over here, we would have to start somewhere on the curve, call that t is equal to 0, and then we'll just travel along that curve. So here's t is equal to 1, 2, 3, 4. Of course, we could also go backwards in time, and that's what we think of this as a time parameter. And that would give us a different way to describe not just a curve, but motion along that curve. We might do the same thing here. We might say this is t is 0. This is us after we've traveled pi over 2, pi, just like the unit circle, pi, 3 pi over 2, and then also we loop back around at 2 pi, and then just keep going around the curve like so. And this is what we call parameterization. And what we would like to do is get a rigorous idea of what this is, and then how can we work with these sorts of parameterizations. So what's really going on here? All right, well, for each of these points, I'll take this point right here. Oops. Okay. So this point right here has an x value and a y value. And what we'll do is, because we're at time 3 at this particular point, we'll call that point x at 3 and y at 3. Same thing here. Here we have the point where t is equal to 3 pi over 2. So that point would have the ordered pair x 3 pi over 2 and y at 3 pi over 2. Of course, these functions x and y would be different for these two different curves. And so, this point on this curve, that would be x at negative 2, y at negative 2, so on and so forth. All right, so what we have here, as I said, are functions. We have a function that tells us the x value for every t value, and we have a different function that tells us the y value at the given t value. And so to parameterize a planar curve, we have two functions. We call those x of t and y of t. All right, and then those are what we call the system of parametric equations. All right, and then we have a certain, what we call a set of points, x of t, comma, y of t, and t belongs to a certain interval. I'll talk about that in a second. That set of points is the parameterized curve, or a parametric curve. Fix my spelling there. All right. So what does that mean for t in the given interval for that parametric curve? And I'll talk about that in a second. We take all the x values spit out by the x function, all the y values spit out by the y function, and that gives you all the points on the curve, including the points in between. This would be the point maybe t equals 3/2 between 1 and 2 here. And we would pick every single real number, and that would give us the entire curve. All right, what is this t? First of all, this is the symbol n. That means t belongs to the set I. The set I is is some interval of t values, and that could be all real numbers. That could be, for example, for this curve up here on the right, we start and stop at the same point, 0 to 2 pi, and we could keep looping around over and over again, but we could also say maybe t belongs to the interval from 0 to 2. All right, so that's the quick overview of what a parameterized system of parametric equations is and the parameterized curves they could produce. Notice that there's a lot of flexibility here. It doesn't have to be a function of x. It doesn't have to pass that vertical line test. In fact, anything you can describe as an equation or as a function of x can be also described with parametric equations. And so they're very powerful tools to use. Let's do a couple of examples where we use these things. I'm going to plot the parametric curve x is a function of t that happens to be cosine. Y is a function of t, which is in this case sine. And the interval of t values will be the same as I mentioned just a second ago. For this problem, it happens to be t ranges between 0 and 2 pi. And we're going to do that first by using a chart. And instead of a chart of just xy values, we're going to have txy values. Okay? And then we'll do it by expressing the curve as a equation, not a function, but an equation of x and y. Alrighty. So how are we going to proceed here? Well, just like when we're plotting functions, usually the easiest way is just to get a chart of a bunch of x and y values, and here there'll be t x and y values, and just plotting the points and connecting the dots. So we'll do that one first. So if I don't know anything about these parametric equations, x equals cosine t, y equals sine t, I'll make a chart of t, x, and y values. And we can pick whatever we want for t, except that it needs to be between 0 and 2 pi, and we should pick things that I know how to plug into cosine and sine. So I'll do the usual suspects, t 0, pi over 4, pi over 2, and since I'm going to go off screen, we're going to have x is cosine of t, y is sine of t. All right, so let's complete this chart of values. Cosine of 0 is 1, sine of 0 is 0. Cosine of pi over 4 is root 2 over 2, same for sine. Cosine of pi over 2 is 0, sine of pi over 2 is 1. We'll keep going. 3 pi over 4. That's going to be a negative root 2 over 2 for cosine, but positive for sine. At 4 pi over 4, which is pi, we'll get negative 1 and 0. 5 pi over 4. Again, both of them are negative root 2 over 2. 3 pi over 2, we'll get 0 and negative 1. 7 pi over 4, we will have positive root 2 over 2 and negative root 2 over 2. And then finally 2 pi, or back to where we started, 1 and 0. Okay, so there is my chart of x and y values. I don't know anything about the curve yet. All I was able to do was just kind of naively plug in t values from the interval, or you can call this the domain of these parametric equations. And we plugged them into x and plugged them into y, and now all I'm going to do is just plot these points and connect the dots. Okay. So at t is equal to 0, I have 1 comma 0, which I'll put right here. All right, at pi over 4, I'll have root 2 over 2, root 2 over 2. I'll get 0, 1, x is 0, y is 1 at pi over 2. And I'll just go around. Now, if you're not sure exactly what that's supposed to be, you could continue on plotting points, and you can make plug in more t values, and you get these intermediate points here, 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 here. Take my word for it. And of course, at the end of the day, what are we dealing with? Well, remember, make that look more like what it's supposed to be. This is what is the shape where x is cosine, y is sine? This is, of course, the unit circle. And so the unit circle is simply a pair of parametric equations. We take our angle, we take our t value, and then the x and the y tells us cosine and sine, respectively. Okay, there's another reason to believe this is the unit circle. So this was my success in using a chart of t, x, and y values. What about expressing the curve as an equation of x and y? Well, to do that, I'll just take this, I'll rewrite them. X is cosine, y is sine. And what I need to do is combine these equations. For this particular problem, the easiest way to combine these equations is to notice that we need to combine them so that all the t's cancel away. And I have a sine and I have a cosine. I remember this fact about sine and cosine. Sine squared plus cosine squared is 1. And then the inside t's would go away. So what I'll do is I'll just write x squared plus y squared. That would have to equal, and this is what we normally want to do if we have sines and cosines, something along these lines here, because then I have cosine squared of t plus sine squared of t. Of course, that all cancels to 1, and so my equation is x squared plus y squared equals 1, and that, of course, is the equation of a circle of radius 1 centered at the origin, which is, again, that unit circle. And so that takes care of that particular problem. All right, let's do one more example. Okay. All right, we're going to show that we're going to have two systems of parametric equations. All right, the first one we'll call x0 is equal to t, y0, or some people say x naught, y naught. Y naught will equal t squared, so that's the first system, and the second system is x1 equals 2t minus 2, and y1 would be 4t squared minus 8t plus 4. I'm going to show that they share the same parametric curve. Okay. Uh, Let me draw a picture that explains why I think this should be true. This doesn't really help me solve the problem definitively, but if I were to take these and plot both of them, what would that look like? All right. So I could do my chart of tx and y values. So here's tx0, y0, and then I'll do x1 and y1 as well for the same t values. All right, and I'll just plug in nice numbers, -2, -1, 0, 1, 2. Those should be fine because I'm just plugging into nice polynomials. All right, so if I plug -2 into x, well, x naught is equal to t, so I'm just going to get the same numbers. If I plug into y, I'm going to get 4, -1 squared is +1, 0, 1 squared, 2 squared. Over here at x, I'm going to get, let's see, I'm going to plug in -2. I'll get 2 times -2 is -4, minus 2 is -6. All right, plug in -1. It's going to be -2 minus 2 is -4. Plug in a 0, -2, and then 0, and then 2. All right, and then if I plug those same numbers over here into y, it takes a little bit more work, but let's see what that should get. That'd be 4 times 4 is 16, minus a -18 would be, sorry, no, minus a -16 would be 32 plus 4. Oh goodness, that would be 36. Plug in -4, we're going to get, sorry, plug in -1 for t. Remember, we're always plugging in from this column right here. So plugging in -1 for t, I'll get 4 plus 8 is 12, plus 4 is 16. Plug in 0, that's the easiest, that's just 4. Plug in 1, we'll get 4 minus 8 plus 4 is 0. And then plug in a 2, we'll get 4 times 4 is 16, minus 16 cancels, comma 4. And what I want you to notice is that while I didn't get the exact same values, I did here though, so these two ordered pairs are exactly the same. And these two ordered pairs are exactly the same. And these two ordered pairs are exactly the same. So I can plot both of those on the xy plane. Like so. I got 0, 0 is on both, 2, 4 is on both, -2, 4 is also on both. And then I can also plug in these other ordered pairs. I've got a -1, 2. Sorry, -1 that should have been a +1. I've got a +1 right here. All right, and then what else? On the other one, I've got a -4, 6, which would be 16, which would be way up here. I've also got a -6, +36, which would be way up here. And you can see how they shared some points, but if we were to connect the dots, and that's what's important here. If we were to connect the dots, it looks like they both land on the same. It looks like it's a parabola. All right, so let's see why those do, because I'm not a perfect artist. It looks like they could land on the same curves, but I can't keep plugging in different numbers to get the same, all the different possible ordered pairs. In fact, I don't have an interval of t values that I'm told to restrict to, so I can't plug in everything. There's infinitely many things to plug in. So how do I actually show that these two systems are exactly the same parametric curve? And the way I'll do that is by showing that they share the same equation of x and y. So let's make some room so it's easier to do all that. Okay, so let's take both of these. I've got x is t and y is t squared, or x naught and y naught. So what I could do, since x naught is equal to t, I can just plug in x naught in for t. And so that immediately gets me that y naught is equal to t squared, and t is equal to x naught squared. So there we go. Y naught equals x naught squared. Okay, what about the other one? That one's a little bit trickier, but what I can do for here is I can solve for t. So 2t would equal x1 plus 2. T is equal to 1/2 x1 plus 1. Now take that and plug it in up there. All right, so what would that end up being? That gets me that y1 is equal to 1/4 x1 squared plus x1 plus 1 minus, that's 4x1 minus 8 plus 4. Then we'll distribute out that 4 here, here, here. That gets me x1 squared plus 4x1 plus 4 minus 4x1 minus 8 plus 4. 4 plus 4 minus 8 is 0, plus 4x1 minus 4x1. There were definitely better ways to do the algebra than what I did, although this is the most straightforward and it works for almost every problem. And the important thing is that I end up getting that y is equal to x squared in both, from both of these parametric equations. So for both systems of parametric equations, I have the same relationships between x and y, and that tells me that these are sharing the same parametric curve. It's that parabola that I drew just a moment ago.